I just started the lecture. Yeah. All right, guys. So we're gonna start the second one. I will do a second sign-in sheet at the end of class, so just for fun. Yeah. So all right. So let's go ahead and start the video here. I'll use the whiteboard a little bit. I'm gonna address like two things. The different types of machine learning, which are supervised, unsupervised, and semi-supervised, guys. So I'll talk about that. And then we're gonna talk about embeddings also a little bit. So these are important concepts. So I will start with the very basics of unsupervised learning, like the traditional one. Guys, right. All right. So we're recording, so I'm going to go ahead and create a whiteboard first. Okay, so I'll create a whiteboard, and I'll just kind of give you like a classification of machine learning. Okay, so this has changed quite a bit. So in the past, I've done different classifications. I remember when I used to teach this, years ago, I would only say there's two areas: supervised and unsupervised machine learning, right? Now I will say that there's supervised, semi-supervised, and unsupervised machine learning, right? So we're going to talk about these concepts. We've addressed one of them already quite extensively. So I use my whiteboard here. So we have supervised, we have semi-supervised, and we have unsupervised. Okay. Unsupervised. Additionally, one thing I'm going to talk about today is embeddings and actually something called the vector space model. They're like the same thing. All right. So this lecture, I usually they tie in really well. So embedding. I think there may be two M's in there. All right. And then as this the vector space model, VSM, the vector space model. So they're kind of the same thing, right? So these are ideas that we're going to talk about today. Obviously, deep learning relies heavily on embeddings and the vector space model, like heavily. All right, but we're going to talk about supervised, semi-supervised, and unsupervised, right? So all the excitement nowadays is neural networks, deep neural networks, okay? Those are methodologies, but there's these classifications. And what they mean is when we do supervise, the key idea goes back to the first week of class. We have an X and a Y. So that means we have some features that we're trying to learn, and they're associated with some kind of a label, or some kind of a regression value. And so we're going to build a model that correlates these inputs to these outputs. So the example that we just did, for instance, would be Celsius to Fahrenheit. So Celsius to Fahrenheit. Does that make sense? But this can be anything. Could be images, could be text, whatever you want it to be. Okay? That's the key with supervised. Unsupervised, which is actually the topic for today, is only X. There is no Y. Like this does not exist. Instead, one way of thinking about it is that you're trying to figure out methods that will discover this Y, but you just don't really know what it's going to discover. Okay. And so we'll see that because when you say, usually when you hear the word unsupervised, they talk about clustering. But what is clustering? Clustering is I take you guys over here and you guys over here, and I say 1, 2. So then I've assigned effectively a label to you. What kind of a label? I don't know. because I just grouped you by, something. And then some of you are closer to 1, some of you are closer to 2. What is that? It's a latent thing that you don't really know what it is. That's a key word, right? So, but it has something called a latent meaning. And that's what embeddings also have. They have a latent meaning. They learn how to represent things, but you don't quite know what it is. The machine learning algorithm does, though. And so that's kind of the similar idea. So unsupervised learning is trying to learn this. And that's going to be the focus of today's class. Okay? Semi-supervised then is what? Semi-supervised, we have X, usually, and we will have a Y over here, but I'll use a different letter. I'll use this is XA, and this is XB, for instance. So why is that? We do have data. We do have this trick that we can correlate. But the difference, you can take it to be that no one had to annotate the data. So for instance here, let's say for sentiment analysis, right? I have a sentence and I say it's happy. I have another sentence, I say it's sad. I have another sentence and I say it's angry. Do you see that? It was annotated and I will learn those correlations. In semi-supervised, no one has to annotate the data, but you do learn correlations. So what's a great example of semi-supervised data? What you're doing right now, your VetGPT. Why? Because you don't have to annotate that text, right? But it is correlated in a way. So the way that you can think of it is like this. So you have the sentence, and then you have the next word that it's trying to predict. So the next word. So your model effectively is learning to correlate those two. Where do you get this data from? Any text, right? Any text where you have a sentence and then you have the next word. Do you guys see that? So that's basically what you can think of as this idea of semi-supervised. So the way that I define it, at least, is that I don't have to annotate the data. I just use data that's already out there and that is annotated effectively. If I take, a sentence, I can tell if that, the sentence 1, sentence 2, I can tell you if, okay, this sentence definitely comes after this sentence or not, right? If I'm saying, the rocket is going to take off tomorrow, and then I say the dog slept on the chair, you kind of know they're not related. But if I say the rocket is going to take off tomorrow, if the weather's really good, it's related, right? So that's kind of the idea. So you can, this is how GPTs actually work. This is how we, this is like, how can I put this? So these ideas probably have existed for hundreds of years. It wouldn't surprise me because everything was kind of discovered a long time ago, but this was really kind of like the insight, one of the many insights that allowed us to create things like ChatGPTs today, right? That, certainly when I was learning this stuff, I expected the world to be like this or like this. It didn't really occur to me that there was this part of the world. I wish I had this idea because it's a simple idea, and 15 years ago, I would have become famous, right? So, but yeah, these are simple ideas, very simple. I can just grab all the books. I know we knew about next word prediction and all that, but you didn't think of this classification as semi-supervised where you had there's a lot of structure that already exists in the world and you can take advantage of it. Yeah, please go ahead.
Isn't this more like self-supervised rather than semi-supervised, like what you're describing right now?
Self-supervised?
Yes.
It can be self-supervised.
I think as far as I understand, semi-supervised is when you have X and some Y, and then mostly X which does not have a Y. Like
so you mean just a little bit of data?
Corresponding X and then completely unsupervised.
You may be right. I may have misspoken here. It's probably self-supervised. And I'm not familiar with that semi-super. That's what you said, actually. But yeah, so That's fine. So let's correct it as self-supervised. But that's the idea, right? So the idea is that this is certainly in the context of the data that we're learning, the GPT model, we didn't need to have annotated data, thankfully, because there would be too much data to annotate, and it would just be impossible. And also, we can't just like do this unsupervised like we're going to do today, because that would make no sense. So we have to do something kind of in this sphere here, self-supervised. And the idea is there is structure already in text. Like we know what the next word might be or the next sentence, etc. Do you guys see that? All right. So we've done many examples of this supervised methods. Okay. And these are basically when you have, X's and Y's, right? We've done examples using many neural networks. So we did linear regression today, for instance, which is a traditional method, right? I'm pretty sure we've done multi-layer perceptrons. We also did deep learning, right? And so basically neural networks, some linear regression there. We'll do logistic regression, and then maybe one more method like XGBoost or something like that. So it might be one of the last methods of the traditional spectrum that I will cover, but certainly we've done this. Now, supervised can be both for regression or classification. So whether we're predicting a temperature or we're predicting a label like a cat and a dog, right? So that's the more traditional example. Then we have, as I was saying, this self-supervised, and basically the idea here is going to be GPTs. That would be the classic example of this. I can take any text in the world. You guys, in fact, for instance, think about the project that I've given you. I didn't say go and get a whole bunch of images and annotate them, right? That would have been a lot of work, and at most you would have produced 1,000 images, at most. With this example, you're really not limited, right? So you can collect. Someone was asking me how much data should they collect. Well, really, you could have collected a lot, could collect an infinite amount of data. But the problem is, are you going to have enough memory, enough GPU power to process all the data? That's really the issue. So that's the advantage of this methodology. Okay, and then, so I kind of wanted to do this contrast today before I actually focus on this one, unsupervised learning. So this is a technique unlike this previous one, right? So here we literally don't have anything to correlate to. So then we have to use other methods, right, of learning. And then in essence, what we're basically doing is we're going to take the data in here and kind of group it. And that gives us this intuition of creating labels and so on. Does that make sense? All right. So so I've mentioned that. So we're going to focus on this methodology on supervised learning. And also I will start touching on the idea of vector space models and embeddings as part of that whole process. So we're going to take text and we're going to think about how to represent that text and build from there. Okay. Any questions? All right. So we're going to switch over to the now that we have a little bit of background here, we're going to switch over to the code. Okay, so I'm going to stop that one. And I'm going to share the screen. All right, so I will create a new Jupyter notebook for this one. We're going to think of the problem. Okay. All right, so I'm going to do new here, Python. And I'm going to call it unsupervised. Today, I'm not going to focus on the algorithm, because if I go into the algorithm, it's going to distract you from like the thing that I'm trying to do. So instead, I'm just going to use sklearn for this. So I'm sure you guys have heard of sklearn. So this gives me an opportunity to use it in the course. And it's really about what we can do with unsupervised learning. Okay. So we're going to go ahead and get started. So I've called this unsupervised. All right, so we're going to need some library. We're doing basically something, it's like a latent semantic discovery. And you will see this word a lot in machine learning, right? The latent vector. That's going to be in it. We're going to touch on this idea again. In particular, autoencoders, for instance, do this. You know, embedding machines like the GPT encoder do this. At the end of the day, it's just a vector. And that vector learns these values, right, that represent something. Okay, we've done it already with the nn.embedding, right? We've talked about it already. So I'm just kind of building from like a very basic thing to where we're going to go. All right, so this is going to be a text-based example. So latent semantic discovery. And we want to find relationships in this example that I have. Oops. All right, so let's go. And this, you know, I'm going to use at some point, it's like a two-step process. So first, the latent semantic discovery of vectors or vectors, let's say. And then the algorithm is called K-means. So not KNN. So there's something called KNN, right? I don't cover that one in this course. I cover that in like the undergrad level class, 365. But here in, you know, this is not KNN. This is K-means. It's similar, though, to KNN, like a similar idea, but it's got a different objective, right? So the objective here is to create these clusters, these groups of data. And we're going to use sklearn to help us understand it. So I'm going to go ahead here. So import sklearn. Not sure if that one's available here. Should be, right? Because we've been using it for the metrics, I think. All right, perfect. So we've got sklearn, and then I will add things as needed. We might need pandas, so I will add pandas. Import pandas as PD. Let's import NumPy just in case as NP. Okay. All right, great. So we have, okay. Now, the key thing I'm going to do is I'm going to have some data and I'm going to try to cluster it. Okay. My data is going to be, as you know, the theme so far has been text. So it's going to be some text data. All right. And we're going to start building up. So I'm going to do several sentences. So I'm going to do 7 sentences. So the first sentence is going to be machine learning. Machine learning. Machine learning is super fun. Which I'm sure you guys agree that it's super fun. All right, then Python is super, super cool. Python Python is super, super cool. Then I'm going to do statistics is cool too. Data science is fun. Data science is fun. Python is great for machine learning. or machine learning. Okay. I like football. And finally, and I'm missing a comma. And finally, football is great to watch. All right, that's it. So that's my data, 7 sentences, right? I ask you the following question. Read these sentences and group them into 2 categories and tell me what you think those categories would be. If I asked you that question, what would you say? Read these 7 sentences carefully and group them into 2 categories and give me the label of that category. What would you label them as? What do you think? No?
Relating to football and relating to data science and machine
learning. Right. So which ones belong to football? The last 2. And then the first 5 belong to like machine learning, right? How did you guys do that? You have your neural network over there, right? Right? So you're human, right? You're intelligent. You're not AIs. But you did it, right? Somehow you did it. You came up with the groups. So you could say I'm going to label the first 5 as 1, the last 2 as 2. And then also, though, you said sports and machine learning. The first step is easier. The second step, arriving at that label, Noah said, I think machine learning, right? He said football. I would have said sports because I just wanted to generalize more. But at the end of the day, that's the latent meaning that I was talking about. This word latent here, latent semantic discovery, all of us somehow did that. Machine learning is also trying to do that, but it doesn't quite know how to say. It can say, oh, the first 5 belong to class 0, the last 2 belong to class 1, but that's easy actually. But saying that 0 is machine learning, the other one is sports, that's harder. But the meaning may be there, right? And it's a latent meaning that you don't really know what it is. Okay, it's a pretty important concept. All right, so what we want to do now is we want to take this data basically and do just that. Repeat what you guys did, but with the algorithm, right? So we want the machine learning algorithm to do this for us. So the key thing, though, is that we have sentences, and we need to convert these sentences into something, a vector, because machine learning only understands vectors, as you guys saw at the beginning of the semester when we were talking about tensors. So the vector approach that I'm going to use is like the easiest one that I can use here. But we have more advanced ones like embeddings, for instance, which are much more powerful because they have a lot of latent meaning from the world. Okay, so we will explore this later in the semester as we start looking at autoencoders and things like that. But for now, we're just going to use the simplest approach. And that's why one of the things I'm going to demo today. So let's go ahead and run this one. And we're just going to use some libraries from sklearn that are very good for this task. So the library that I'm going to use is something called the count vectorizer. Okay, so I'm going to import that from sklearn. So let's add a library here from sklearn dot feature extraction. And this may have changed. So feature extraction dot text import count vectorizer. Okay, so let's try that. Okay, no errors, right? So it accepted that library. So this is what 15 years ago everyone did, pretty much. That was the state of the art back then, right? What we do today is way more sophisticated with this idea of embeddings. All right, so let's go ahead and now convert basically our text into some kind of vector representation. So I'm going to create an object vectorizer. Vectorizer. I'm going to instantiate it from count vectorizer. Okay, I'm going to say min df, and that just means that the word needs to appear in at least one sentence. So I'm going to do min df equal 1. Stop words in this case going to be English. So what that means, it should ignore things like is, the, etc. And just because we're only looking for meaning in this example, right? So I'm going to do stop words equal English, like that. Okay, so let's do this. Okay, no errors. That's good. So we've got our vectorizer initialized. Now I'm going, and I called my data examples. So now I'm going to train this model. I'm going to do DTM vectorizer dot fit underscore transform. And what am I going to train on? Train on example. So basically I'm asking it to learn how to convert that text into something that machine learning can use, right? Which is going to be creating some kind of a vector. In the future, we'll do pretty much the same thing, but with more advanced techniques. Okay. Examples is not defined. Misspelled? Oh, yeah. Thanks. Samples. All right. So run it again. All right. So train. Perfect. You guys see that? So now I'm going to display this as a pandas data frame. So I'm going to say DTM PD, for pandas. And what we want to do is we want to look at each of these sentences represented as a vector. Okay. So that machine learning can use it. So we're going to say PD.dataFrame. And then we're going to give it DTM, which is this variable over here, dot array, like that. And we also want to provide the sentence. So we're going to put sentences in the row section and then the words in the column section so that we can see how everything is represented. So I'm going to do here index equal examples, comma, columns equal, and this is going to be the feature names. So it's going to from vectorizer, from vectorizer dot get feature names. Like that. Okay. So get feature names. Right. And then just so that we can actually view this, I'm just going to limit it to about 10. So I'm going to say head. It's going to be 10. Okay. All right. So if everything works, this should print out. Doesn't like it. Array not found. DTM array. Oh, two are right. I'm sorry. Get feature names. Okay. All right, so definitely want to get that. Am I misspelling something?
The internet, it says there should be an underscore out as well after the names. After names, underscore out.
Okay.
OUT out.
Oh,
Underscore.
the word out,
Yes.
underscore out, you mean?
Yes.
Oh. Thank you so much. All right, perfect. So yeah, so there you go. All right. So we have our pandas data frame here, right? And what does this give us? This is your first vector representation of words or sentences in this case, right? And this used to be the state of the art even 15 years ago. This is what you would do. This is called sometimes the bag of words approach. All right. And basically, there's some serious problems with this, but this is how we used to do natural language processing, document retrieval. Maybe you guys have heard of something called RAG, which is, something augmented retrieval, etc. All these things. But it all started here. So what's happening here is I'm taking the sentence, machine learning is super fun, and I'm just representing it as a vector of the keywords in there. Think about how crude this is. This is something that a human can do without having any machine learning knowledge, right? You're just like, okay, that's 1, 2, something. All right, so in this case, I have cool. So I have like a vocabulary, right? Cool, data, football, fun, great, learning, like, machine, Python, science, statistics, super, watch. And then I'm kind of counting. So notice, for instance, this one has a count of 2, right? And then whenever you want to represent the sentence, statistics is cool too, you just grab that vector. And they all have the same column names, right? So for instance, for all the sentences, football is the third word. Do you guys understand this? So now we have taken our text. Now, is this how GPT works? Hopefully you understand that it tries to create embeddings, but it doesn't work like this. It's got a more sophisticated mechanism, right? So what are the downsides of this approach? This looks reasonable, but what if my vocabulary is 70,000 words? What's the problem there? Every sentence will now be represented by a vector of 70,000. That's not fun. What's the other problem in that vector of 70,000? The majority of the values are what? Zeros. And then there's very few ones. I was doing some work. I showed it to like a colleague of mine, looked at doing something like this. They looked at the screen. It was like, it's all zeros, right? So it could happen, right? You're looking at a specific part of the thing. It's all zeros. So the point is, this was a big problem, okay? The vectors had to be really big. They roll zeros with a few ones. Okay, so that was not a good approach. What did people want? People wanted, this is called a sparse matrix, by the way, sparse, right? What did people want? They didn't want vectors of size 70,000. Instead, they wanted vectors that were way smaller. What was the size of the embeddings of our GPT? You guys remember for the tokens that we did? 512, right? 512. That means literally 512 columns. Whereas this one has about 10 columns, but if we had an actual, many sentences, our vector might be of size 70,000. And it would be very sparse. So the other thing that happens, the other solution is that is 512, but they're very dense. What that means is there's no real zeros in there. Instead, all the columns have values. You guys see that? So that's a contrast between this approach, the bag of words approach, and the embeddings of today. All this revolution of embeddings, I'm sure it was invented many years ago, but it came about around the time that something called word2vec was invented, right? So that algorithm made it very popular. And the key insight was that the vectors were no longer 70,000. They were just 512. They were no longer sparse. They were dense. And they basically represented these ideas of latent semantic spaces, vector spaces, etc., that we're going to touch on later. You should be convinced that this is like a dimensional space, right? In this case, it's like a binary, not binary because there's some that have a 2 in there, but it's definitely a space. Just not a space like our known 3-dimensional space. This would be an 11-dimension space. And every single one of these sentences would be what in that space then? A point. Do you guys see that? So now I have this sentence, and I can tell the distance between them. That's kind of the goal whenever you create these ideas, these embeddings, these latent semantic spaces, etc. And this is an underlying concept in GPTs. They are actually trying to learn these values during the training, right? If you remember, I said that the NN embedding initializes everything to random values, and as the training goes by, those things are populated. Okay, but initially we start here. And actually, we'll be able to solve this problem with this approach. Okay, so it's not like it's useless. It is useful, and people have invented many interesting algorithms. There was one TF, IDF, etc. So certainly, people use for information retrieval, document discovery. This was very popular, like in magazines and things like that. All kinds of things. So anyway, but I've been able to now encode my data into these latent these vectors, basically, by using the count vectorizer. All right, so hopefully that made sense. Okay, now let's move on. So I have my 7 points in this space. Okay, now the next thing I want to do is I'm going to let's see. Let's plot this, okay? How do I plot these sentences in something that I can see? So there's a problem with this data, right? And the problem with this data is that it has really 11 or 10 dimensions. But humans can only see things in 3 dimensions or less, right? So unfortunately, we cannot really plot it in this space. But we can do a projection like the ones that we were discussing in the 109 problems I gave you at the beginning of the semester. In this case, we're going to do a projection to a smaller dimensional space. We're going to use a technique called truncated singular value decomposition from sklearn. And basically, this will allow us to kind of like make these vectors smaller so that we can plot them. And we're going to hope that a lot of information is retained in these truncations so that we can actually plot our data. Okay, so that's the first thing that we're going to do. And then after that, we're going to apply the K-means. Now, I'll tell you right now, if you're excited about this technique, this usually works for simple things. But when you have a very complex data set, performing these kinds of compressions lose a lot of data. So you really can't make out what's going on, but it's certainly something worth trying. All right, so I'll just make a note over here. I'm going to use something called truncated singular value decomposition to calculate, to do this compression, okay? So let's go ahead and do that. And then my goal is really just to plot it. Okay, so I'm going to create an object here, LSA, let's call it. And I'm going to use an object that I need to import called truncated SVD. Discussing how singular value decomposition works is outside of the scope of the course, is quite heavy on linear algebra operations. All right, so I'm going to do that. I'm going to say that I only want two. I'm going to compress. So the intuition would be that instead of having 11 columns or 11 axes in a vector space, I'm going to compress it to something that only has 2 axes. So it's like, imagine if I was compressing something from 3D to 2D. So what is that? That's like taking this space and projecting it onto this page. So a good analogy of this is I can have you, right, in the space, or I shine a light on you, and your shadow is what is on the page. So think of it that way. Does that make sense, guys? Like, so like a child and an adult, right? So I can obviously distinguish them here. I see a child over here and an adult over here. But if I shine a light on the child and then I see their shadow on the page, versus shining a light on the adult and seeing their shadow on the page, I can still tell which one's the child and which one is the adult, right? So it's kind of like that. Okay, so that's what we're doing. It's like we're shining a light on the object in the 11th dimensional space into a smaller 2-dimensional space, and hopefully we can still see a shadow of the original data. Okay, that helps us in our problem. So let's go ahead and try this one. So I'm going to do LSA truncated SVD. Oh yeah, and I haven't added it, so I need to go over here. I'm just using sklearn, so it should be from sklearn dot decomposition import truncated SVD. All right, so hopefully no errors there. Okay. And then down here, I instantiate the object. Okay. All right, so I've got my object here, and now I'm going to apply it to my data so that I can basically convert this pandas data frame into a smaller pandas data frame that I can actually see. All right, so I'm going to create DTM LSA, and I'm going to use LSA, the object I just created, dot fit transform. Okay, transform, I think that's spelled correctly. And then I'm going to give it my original DTM over here, okay? Yeah. Just like that. All right, so once I do that, okay, no errors. Okay, so I have it now, and now I'm gonna go ahead and convert it to a pandas data frame and print it, right? So hopefully I can actually probably copy paste this one, just change the name and a few parameters. So let's see. So I'm gonna call this one SVD, just so I don't confuse it. SVD, singular value decomposition is a technique. All right, I'm gonna do a data frame. The input to it is gonna be DTM LSA. So it should be that DTMLSA. Okay. The index now would be examples. That's still the same thing. Now, obviously, what has changed in the columns? So before we had 11 columns, which were the words, right? But these no longer exist. Now I'm only going to have 2 columns. But those columns are a result of looking at these 11 columns. So the simplest intuition is I'm going to create, so imagine I have, these are word 1, word 2, word 3, word 4, right? So the simplest intuition is I'm going to create component 1, which is a linear combination of W1 plus, and I guess I need to say W1 plus W2 times, oh, this should be what? Word, right? So let's use a different, instead of word, I'm going to say what? Term. So T1. And then this is W2, T2 plus dot, dot, dot plus WN times term. Does that make sense? So this is probably the simplest way of understanding this. There's more going on with singular value decomposition, but you can think of it as somehow I took the words, figured out some weights or something to create a new representation of them. And then I'm going to do that twice. And now instead of representing each of these sentences by the 11 words, I'm only going to represent it by 2 columns. What do those columns mean? I don't know, because they are latent. You see that? Again, that term. The machine learning algorithm, though, might be figuring something. See, this is where AI, right? We're scared of it. Because what is it discovering? What if it discovers something that humans never thought about? That kind of thing. Anyway, so I have to change that. Oops, I have to change this. And I'm going to put a comma in here. So I have to change this columns. And instead, I'm just going to give it a list. And I'm going to say component 1. And this is probably, double quote. So I'm going to say, actually, I'm going to say SVD1, just so that you guys remember that this is coming from there. SVD1. And then I'm going to say here SVD2, okay? So that's it. So basically, I asked it to discover 2 things. I can label it whatever I want because I actually don't know what it is. All right, so let's try this one. Okay, didn't like it. Oh, to array. Get rid of that. Try it again. Okay. Does that make sense, guys? What I did there? So I started with, I'm doing embeddings, just like GPT, wants to do embeddings. I took 5 sentences. Machine learning does not understand sentences, so I convert them to some kind of vector of a specific size. I'm using the bag of words approach, so I have this. Now, let's say it was 70,000. So if it was 70,000, maybe my laptop just doesn't have enough memory to handle 70 vectors of 70,000. So then I can also compress it, right? We know that compression allows things to run faster. So that's another reason why you might want to do that, right? So you can compress it, or you can do, as I said, you can compress it basically. So I've done this this approach, and just I said I wanted to. Oh, the other reason is to plot it. Okay, so notice that I still have 7 sentences. So this is a matrix that is 7 by 11 or so. This is a matrix that is 7 by 2. Another way of thinking about this is I projected this to another space, a latent space, because there's still going to be points, right? Every sentence is still a point, but this is another space. We can do this trick all day, right? We can project to smaller things, to bigger things, the support vector machines. So this is probably the only thing I'll say about support vector machines. is that they did the opposite. They would take something in a space and they would actually project it to a higher dimensional space and put the points there. Why? Because they thought, okay, if we project it to a higher dimensional space, more features means that somehow there's more opportunity to learn, and they wanted to use a linear model, you know, like create a line instead of a curve or a neural net kind of a thing. Okay, so anyway, that support vector machines would project to a higher dimensional space. So instead of 11, might project to an infinite, you know, or 1,000. But hopefully there's more room in there to learn. Do you guys see that? Anyway, so I don't want to get too far from where I am. All right, so this one is 7x2. One advantage of this one is we can probably plot it. It'd be nice if every problem somehow we can just, you know, shrink it to this and then like visualize it, right? But unfortunately, it doesn't always work that way. But in this example, this is more of an academic example, so it should work for us. So what I'm going to do now is I'm going to plot this graph. And then, as I said, my ultimate goal is to cluster it into science-y things and sports-related things, the latent parameters. But I want my machine learning algorithm to discover that. So I'm going to do plot over here. Okay, so I'm doing plotting. Okay, so I'm going to hit kernel. I'm going to, oops, no run. Okay, so plot. All right, so how do I plot this? Again, if you guys like plotting and want to learn about it, we have a course called Visualization by Professor Jin, so you can take a class with him. All right, so I need some data, and I'm just going to use a scatter plot, basically. Okay, so I'm going to create XS, YS. Okay, so from DTM, I'm going to grab the columns. That's it, and plot this data. So it should be pretty straightforward. I'm going to do a list comprehension for W in DTM LSA. And that's just going to be W, but column 0. Okay. So I'm grabbing, you know, this first column and then that column. That's a 2-dimensional space. So effectively, I took something that was 11-dimensional and I'm projecting it to a page of 2 dimensions. Okay. So I'm going to do the same for the next one. This is going to be, what is it? W's, sorry. W1 for W in DTM LSA, just like that. That should be all the data that I need. So I'm going to go ahead and run this one. Okay, perfect. Now I'm going to create, I should have matplotlib here. So I'm just going to say from matplotlib dot pyplot as PLT. Okay, let's see. Hopefully that's it. Okay. And a dot. Did I say something wrong? Yes, thank you. Import matplotlib dot. Okay. Okay, perfect. All right, so we've got our library. So now let's go ahead and print it, plot it. So let's see. All we need PLT dot scatter XSYS, comma YS. And then also I'm going to put some labels in here. So I'm going to say PLT dot X label, guys, shh, guys, down. All right, X label. All right, so one of these will be the I think we called it SVD1, right? So SVD1. And then I'm going to do the same. Y label. And that should be SVD2. All right. And then PLT.show basically to keep this simple. Okay, so let's go ahead, try it. Okay. Right. All right, there it is. Okay, so if we follow the data, right, it's likely that these four over here, well actually, let me say it this way. If I ask you to grab a pen and circle these dots into two groups based on how similar they are, how would you do that? Like, what would be your circles here? So you'd probably circle this one, right? And then possibly this one over here. So how do you know how to do that? You just know, right? You just know that, okay, these items seem to be closer, so I'll probably create a circle there. And these seem to be closer, so I'll create a circle. You don't even know how you do it. Well, the K-means algorithm actually will do exactly that too. Okay, so that's an algorithm that's clustering. That's what clustering is doing. This isn't, as I said, a discussion of the vector space model. So we're thinking, we were in an 11-dimensional space, and we certainly can do it in that 11-dimensional space, but it might be more intuitive to do it in this 2-dimensional space. And it kind of works here, thankfully, but this is an academic example, and more noisy data, it's going to be much harder. But anyway, we have our plot. So what I would want to do is either create a circle around these and a circle around these. I definitely don't want to circle these two and then these bottom ones, right? Because that's not really the intuition. The intuition is that I want the data science sentences to be together and the sports sentences to be together. So anyway, we've plotted everything. Now we're going to go ahead and in the time that we have remaining, use the K-means algorithm to basically cluster these samples, okay? So instead of discussing the algorithm, I'm just going to use K-means. So let's go ahead and do that. And maybe it'll work, maybe it won't, right? So we'll see, right? So, all right, so let's create, I'm going to need K-means. So that should be from sklearn dot cluster import K-means, just like that, right? So I think that's all we need. So let's see if the library works. Okay, we got the library, K-means. So now we just have to figure out how to feed the data into the algorithm and have the algorithm give us the information that we need, and then we're going to plot it again. Okay. All right, so now the algorithm has some default parameters. I'm just going to use the default parameters of it. It's got, several things in there. So I'm going to do KM for K-means, LSA. And I'm going to instantiate the object. So K-means. Okay. All right, so the parameters are going to be, this one is easy. I want 2 clusters. Two clusters. Okay, I had said that. I wanted to find, group the sentences that have a meaning in science and the ones that have a meaning in sports. Okay, init random. So that just means that I don't have to like figure out where to start. So I'm just going to say random. Do this like 10 times initially and in it. Or you can provide initial values, but I'm going to let it figure everything out. Maximum number iterations. Maximum iter is going to, I'm just going to do 300. Obviously, you can change these parameters. It's got a type of a epsilon value here, which is TO1. And I'm going to set that to 1e minus 0.4. And then finally, the random state is set to 0. So the way that randomizes. All right, so let's see if that works. Okay, doesn't like it. Gonna comment that one out. Okay, so I'll use his own default value. Now let's fit the data. All right, so I'm gonna take what? I can choose the data to use, right? So since we're plotting, let's use the compressed data. And let's just see what happens. So I'm gonna use the compressed data. As I said, in some cases, the compressed data would have lost too much data, right? So you would have to work with the original data, but in this example, it might work, or maybe it doesn't, right? So now I'm going to do Y LSA. Why am I calling it Y? Because if you think about it, finding these clusters is effectively as a type of a classification in the sense that I'm labeling that these belong to 1 and these belong to 2. You see that? So it's kind of like a class prediction. But the clustering algorithm is figuring that out. So I'm going to say KM LSA dot fit transform. And I'm going to give it the data, which should be DTM LSA. Okay. So now, right, so let's now run it. It finished. Okay, great. So let's see what's in Y LSA. Right, let's see if it has a shape. 7 and 2. Okay. Let's run Y LSA here. Oops. So it gives me that. Why do I get 2 columns here? Got 7 values, fit transform, and clustering.
What were you?
Add the labels. So trying to think what it did. So there's the 7 is obvious, right? So we started with these. That's the representation of each sentence as a vector of that. It's not a probability of belonging to a class.
KMLSA, KMLSA dot labels.
KMLSA dot labels, yeah. Yeah, no, it's a good observation. I did. Oh, I did. Oh. Sorry about that. Sorry about that. All right, yeah. So not fit transform, but fit predict. All right. So yeah. So here we have our. So what do we have there? That's actually the prediction. That's the clustering. What do you guys think? Can you guys do a better job than this? Yes, right? The first 5 sentences should belong to one class, and then the last 2 should belong to the other class, right?
Which one did it say?
It should. So I would say that this is the second sentence. So the second sentence is Python is super, super cool.
I'm guessing because it has 2 of the same word. And it's the only one with
The only one. So yeah. I'm not disagreeing, right?
that was the only one.
The only one with 2. That's a good observation, right? So no, that's really great. So how do we solve this? Long way. Okay. I like that. I like what you're doing there. All right. So how do we solve this problem? So what's the problem? Is it that K-means is not working? K-means works. It's just our data is, you could say, it's too noisy, not enough data. So how can I show you that this in fact works? Well, actually, Noah kind of has a good idea. Noah is saying one has super in there twice. And that's important somehow because it's stressed as value too, right? So I can take your idea a little bit further by doing the following. Machine learning and Python are super fun. Python is super, super cool. Statistics and data science are cool. Remember that the R's and the is don't matter because the stop words, they're stop words, so they're being removed. Data science and Python are fun, right? Python and machine learning. Oh, Python is great for machine learning. Okay, let's leave that one. On the other category, what am I going to say? I like football and it is great. Football is great to watch and I like it. Do you see what I'm doing here, right? So I'm just looking at words that are common in one group and like trying to populate all the sentences with them. So now, hopefully, the model is going to work a little bit better. And you guys think about this. You can give me probably suggestions of how to make this even better, right? But I'm going to try to run it again and see what happens, okay? So I'm going to go ahead and run it. Oh, what did I do? This one here? That's the only one? Okay. Okay, perfect. So I'm rerunning everything. Okay, so we still have this one that dominates with 2, right? And then let's try singular value decomposition. There's the plot, it changed a little, you notice, but it doesn't matter because the algorithm is, going to look at the data as is in the vector space and try to figure out the groups. Have my 7 there. Did it? Did you guys see that? It worked, right? This time, the first 5 are 0, labeled as 0. The last 2 are labeled as 1. So basically, I was effectively able to predict also 2 categories, just like you guys did. The only difference, though, is that these are latent labels. The machine learning algorithm is not a person, right? So it doesn't know that one is data science, the other one is sports, but it does know that they're similar. And all it took for me to get this to work is the correlation of the words. You can see how it learned. And that's what GPT does, right? GPT, knows the words around its context, right? And it does it with so much that it actually knows meaning. Maybe it has not only the grammar of English, but a grammar of understanding. You don't know, right? So anyway, so that's kind of the idea. All right, so the last thing I'll do is, let's plot it to kind of complete the exercise. But if you see, we've achieved our goal. I have discussed unsupervised learning. I have shown you what is unsupervised learning. There are no labels, right? Not self-supervised or supervised even. This is just just look at the data in a vector space. This is key that you guys understand because this is how I usually introduce the vector space model. The next thing that I will cover is, not today, this idea, but now with embeddings, right? And I've given you the motivation for that. We don't want large things. We don't want sparse. We want kind of small. So there's word2vec. How is word2vec trained? With an autoencoder, which is a neural network, and so on, right? So there's quite a bit that's going on. All right. But it all comes from this idea, and then people, just very smart people, figured out things efficiently. All right, so in the end, each one of my sentences now has a label. So the first 5 would have, so now this is X and Y, right? So this would be, for the Y, 0, 0, 0, 0, 0, and then 1, 1. Done. But they are, as I said, latent variables. So the model does not know that these are sport or data science. All right, so let's go ahead and plot this now. Should be. So my data is in X and I have labels, right? So I'm going to do PLT dot scatter. Okay. Parentheses, close parentheses. So I'm going to plot X for the 0 column. And I'm going to plot X for the Y column. You see that? So that's similar to the previous one, but I just need to index it by the label that I'm assigned. So in this case, I'm going to say, because they have the same dimension, I'm going to do Y LSA equal to 0. So these are going to be the 0 ones. Y LSA equal 0. So I'm just going to slice out all the 0 ones, so the first 5 basically, right? From X, and I want both columns, and I'm going to plot them with a specific color. So I'm going to go ahead. Comma, and I'm going to say, I think this is size, so S equal 50, comma, C is going to be the color, light green. Marker will be marker. is going to be star S, and label will be cluster 1. Actually, I'm going to say latent 1, so that you know actually that the model doesn't know what it is, but it created this concept. These discoveries that the model is doing, right? All right. So that's that should be it. And then I'm just going to copy this for the next one. Oops. Copy. Control V. All right. So I'm going to do here. All I want is that these should be for the class 1. So the last 2 sentences. And I grab the X and the Y. S is 50. I'm going to change the color to orange. The marker is going to be O. And this I'm going to label as latent 2. Right? The other thing it discovered. Okay? And now I'm just going to go ahead and hopefully this will plot PLT dot legend PLT dot show. All right, so that's just, I mean, you guys, oh, okay. X is not defined. What was the data called? DTM-LSA, I guess. Yeah. Right. There you go. So, I mean, this is just more to make it pretty and everything, but that's the idea, right? So it discovered the sentences like this, right? So latent 2, that category, orange, whatever it is, probably the 2 sports. Well, we know, in fact, it's the 2 sports related sentences. And then these 5 over here in the light green are the science related. The 2 latent terms, you guys, because you're human and smart, know what they are. The machine learning algorithm doesn't quite know in such a simple algorithm, but a GPT or so may know a little bit more. Okay. All right. Yeah. So it's 7:40. I'll stay for 10 minutes if you guys have any questions on anything. Otherwise, this concludes one of the traditional methods that I wanted to cover today, which was unsupervised. I also wanted to use this example to start talking about embeddings, latent vectors, all that, the vector space model. So we've discussed a lot, in fact. You've seen the technique called K-means clustering, not the algorithm itself. So I may skip that algorithm. You can take 365 if you want to learn that. Yeah, so that's kind of the example. Please don't forget, a week from today is your exam 2, right? And yeah, we'll do another lecture and also work on your homework assignment. All right, guys, so I'll stop the recording now.